Okay, and welcome back to the Extremely Open Science. Sorry about that. Extremely Open Science stream. So I want to just get everybody's bearings. We are looking at whether we can find excess of small genes as a metric for genome quality. So because we had this observation that when you have genomes that come from Oxford Nanopore, you have more interrupted genes which show up in your data as having a lot of small genes. So we've been playing around with this, and let's just cut right to it. We've been playing around with this idea by simulating adding mutations to genomes from progenomes. Normally I like to make these have the same size. I'm just getting these to have the same font size. Yes. We've been playing around with these genomes, and let me just show you where we're at. Let me see where we're at. Okay, let's move that way. That was a little bit. And so we've run this so that we get 1 out of every 200 genome, and when we plot this, so when we plot this metric that we have, it looks okay. There's a signal there. There's something there, but it doesn't look as good as it could. And actually, let me just. And it just doesn't look. Let's see. I had. Let me just grab it for you, because I had. No. Just grab it for you. No, instead of recreating it, this is what we got. Right. So this is this metric that we've been using. Z scores below -4, and you can see that there's basically a handful. So the way to read this figure is that on the x-axis you have the number of mutations, and then these dashed lines represent 0.0. So ideally all of the 0.0, so no mutations, would be really up there, so no excess of short genes, and then as you add mutations they go down. And there'll be a very clean separation between the dashed lines and the full lines, but unfortunately that doesn't seem to be the case. At least it's not perfect, right? And so, and actually, just so we had most results for oh yes, but the results are actually there. So, all right. So I've been thinking about this. So a couple of things we could explore. So one would be, can we get maybe some of, you could try to filter out, we've talked about these things, maybe KOs that are not very stable. So that would be one idea, and we've tried to look at this, but now we could use the data themselves to tell us. So we could look at, which KOs are more likely to be false positives. If we consider that everything that's at 0 mutations is a false positive. But actually I wanted to do something a little bit different, which is I'm gonna just switch everything over to, instead of using KOs, from CheckM2, I'm gonna use Eggnog Mapper and use that as a mapping. So for those of you who don't know, so Eggnog Mapper. So Eggnog Mapper, okay. Alright, okay, I guess the website's down. So Eggnog is a database of orthologous groups, so of protein families, gene families, and then Eggnog Mapper is a tool that, you know, given your data set or your set of proteins, maps them to OGs, Eggnog OGs, orthologous groups. So a little bit, in that sense, not so different from what we've been doing with KOs, but very, very different in the sense of it's a completely different database. And also I think, you know, here this was a very simple strategy. It worked very well for CheckM2 because CheckM2 really was only using the KOs as an intermediate step. So, and then that meant that, you know, it could afford to make mistakes there, and it wasn't really optimized for that. So by the way, so last week we had a lot of problems with installing the latest version of CheckM2. I talked to Alex, the first author of that tool, and apparently there was an issue with the content packaging that has now been fixed. That had to do with the auto updater not working perfectly. Right. So, all right. So let's see. So this takes. All right. So let's see if we can do. Yeah. So here in Sardine, add. This is like this. Actually, we should have been adding it to the Sardine environment, not to the. What's okay, perfect. Let's see if we can add it there. So I'm adding it to the Sardine environment, and so in principle this should work, or it will tell me that it doesn't work, but in a slightly nicer way. So Eggnog Mapper, a little bit like a little bit like all of CheckM2, we do need to download the database. Sorry, I can't read that. Yes. Okay, I think we need to, and so I do have it on my computer already. So let's see. Need it done. Okay, so I have to download the data. It's gonna be a while, I guess. Okay, that's not so bad. Not so bad. Okay, we're gonna run everything through Eggnog Mapper. But then the other thing I've been just thinking, so so we've been doing this, so actually now, okay. So we did this thing a couple of weeks ago, where I'm just gonna run one more genome, and so it's always very slow when I have to do this and run OBS, so the streaming software at the same time. But here's Jug running. That's probably on this one. Oops, sorry, this one's there. Jug run. And now it's going to be running checkm2. And so what it does, it generates all of these genomes. Oops, yeah. Okay. Okay, so this is downloading here, and so what I was trying to get to, it's going to generate all of these genomes, and then at some point it calls. At some point, then it calls. At some point, it calls prodigal on all of them, and you have all of these predicted proteins. However, and this is important, many of them are not really, many of them are going to be repeats. And so if we then call Eggnog Mapper on all of them, we're mostly calling them on repeats. And so I wanted to figure out this. Okay, that's unexpected. So much for Pixie is great. Is it still downloading? So much for Pixie is great. I killed those processes. Did I accidentally? Okay, I think I accidentally. Let me do this. Can't hurt, right? Okay. Okay, I think I accidentally copied over something from the HPC. So I did cheat this week a little bit because I ran some of the computations on HPC, which normally, oops, got the camera there. Normally I try to avoid to, but you know, I don't want to be a purist about this. It's, you know, in the end, you know, science takes over streaming. You know, I like this exercise of doing everything on stream, but yeah, if it comes through to the point where I have to choose to do worse science to preserve the purity of the streaming experience, at that point, I'll try to find a solution. All right, there it is. All right, so okay, so we're generating all of these genes, and so this is. And so this is okay, so it's this one, just checking. Yeah, so this is basically just and so what I wanted so what I wanted was to actually, this is probably interesting on its own. I want to just see how often. So what are the changes? So okay, everything's very slow because here we're still downloading the data. Okay, so we had this before. Or, you know, we've been looking at this before. What do we want? So we want sequences. Let's do it the other way around. So, but we would like to see. So let's do this. I need a pen. Alright, here I have my pen. So this is the Muji pen, king of pens. And now, so what we maybe we want something like this, you know, so x-axis is number of mutations, and then 0 is the gene set that we have. Yeah, so let's if we think about it as gene sets, then yeah, let's do it by gene sets. Okay, so we'll do it like this. Probably let's do it as a gene set. Okay. Okay, so the number of sequences goes. Okay. The number of sequences goes up. I think we had seen this, to be honest. Okay, there's something here I don't understand. Because if there's 25 mutations, does it impacts 45 sequences? Or impact, or actually 45 plus 36 sequences. But just for how does the math? I'm sorry. I'm a little bit confused with what's going on. I'm a little bit confused at what's going on, because the difference between 0 and 25 should be much smaller. Oh, look, here's again the partly deterministic random thing we talked about a couple weeks ago. So this will deterministically mutate this one. Okay, I'm gonna Oh, 3, 8, 3, 6. Yep. How do I do this? Okay, I'm a bit confused. I didn't expect this to be that's still running. It's confused. I expected that if we had 25 mutations, we would have 20 interrupted genes. Okay, so this is Okay, so here's the okay, so 13. Okay, so this seems like very standard what you'd expect. Is this the issue that we get these things? Would this explain what's going on? So we have, okay, so here the sequence is good, and then at some point that 98 is completely different. I mean, you know, and then 98 is also different. Okay, so now from one mutations we got 2 new genes. Okay, so that makes a bit more sense. Okay, and then for everyone we have, there's one we miss. Okay, so that makes sense. Okay, this actually might make sense. So 184. Okay, and here again, so this area, probably here a single mutation generates 2. Single mutation generates 2. Okay, alright, here, oh, here a single mutation generates a bunch. Yeah, okay, this is one single mutation and it's messed up. Bunch of genes in a row. Alright, so a nice little smorf there, small proteins for the win. And then that was a mutation. And then it's completely messed up, that one. Oh yeah, so there's a very nice long gene there. Just gets broken up into a bunch of little ones. And then it regains, then it's correct again. Okay. Yeah, that one is already correct. That one is correct. Okay, so this makes a little bit more sense. Alright, sorry for that. Okay, alright, let's go back to our main goal here. Okay, number of sequence goes up. Okay, yep, this is it. Just for to be sure, x plot. Nope. I put them. Yeah. I'm gonna put there the. Okay. Yeah, interesting. This was. I'm not sure. Yeah, this is something we should have been looked at already somehow. So this is the number of mutations or the number of introduced sequences. Okay. The number of introduced sequences. Okay, and I guess our yeah. We don't have very good internet here. I mean, yeah, maybe they keep promising they'll update it, but yeah, so because YouTube's complaining that there's an issue with the internet. So, okay, this is also fine. Okay, all right, we're making a little bit of progress, slowly. But still, what do you? Okay. So. All right. But this is what I wanted to get at. So we have now, this is still, it's very slow. Everything's very slow because I'm doing the streaming at the same time. And actually, maybe this is also why YouTube is complaining. I'm gonna kill this. I'm gonna kill this. Yeah. Sorry, I'm gonna kill this prodigal and check empty. Sorry, I'm gonna kill this properly because yeah. Okay, maybe this is why everything's so slow and why YouTube complains that it can't stream properly. Stream properly. Okay, but. So we got 70 out of the way. In total, they have 363,000 genes, but given the repetition, only about 2% of those are unique. So if we're going to be doing classification, maybe we don't need to do the whole, unique. So so let's go to the MD5 is fine. Okay, let's do this very, very simple thing where we hash the files, right? Or we have. Do this very simple thing. What about this? It's actually, this is what I want. What I want. So this is actually what I want. I get, if I do this, I get all of the yeah, so unfortunately now again we're a little bit running out of time. Time. Okay, so we get this. And then this would be, we would run this through a global mapper. That would be the next step. And then finally, we would be able to see. Yeah. Okay. I mean, obviously, we're not going to finish this today. So. See what do I want to save from this? No, this I don't want to save. Playing this okay, I wanna, yeah, let's remove unnecessary import. Just check through here, only adding eggnog mapper. Let's add it to the ignore file. Okay, here, and Okay, so this we probably do wanna keep for. And today's the 4th. I think this is. I think I can do this. Okay. Okay. It's not a base. Okay, so this. Okay, now the stream is healthy again. I think this means that we were trying to do the computation and trying to do the computation and and the streaming on the same machine is pretty too much. Okay, all right. This is mostly done. It will finish a little bit. Okay. I'm gonna add, so that I'm gonna add to the work in progress batch. So I've mentioned before, there's, if I was working normally, I would not be even thinking about committing this code at all. This is very messy. I mean, it's not messy, but now it's, it doesn't make any sense. It's not integrated with anything. But here I'll put it on a temporary branch. So progress. Okay, so what do I want to do here? I'm gonna Okay, this is what I want. Perfect. I mean, not perfect, but this is not load fast. Yeah, so okay, so alright, so okay, so we did get eggnog mapper to run. Which is a bit unfortunately we did. Alright, we'll do that next week. I wanted to get this done this week where we would get eggnog mapper to at least run. Did I now mess this up a bit? Combine all. All right, since the furthermore, this relationship. In fact, let's do that. Oh, yeah. Okay, we could I'm just really quick. We're out of time. I wanted to get that plot back that we had before. Okay, permutations n reduced there it is. I just wanted to I just wanted to get this back up because I think I'm going to be posting it on the mailing list. Let me just import. It's funny when you misspell import, it always thinks you want to import. You want to import. Oh, this is not the one. Yeah, this is one. Alright, okay, this one. Okay. Oh, sorry, that. Plot. Just one example. Alright, I'm gonna push everything to get, again, we're a little bit running out of, little bit running late, but you know, everything's on GitHub. I'll post to the mailing list as well an update of what we've done. We didn't make as much progress as I hoped today, but you know, we didn't get Eggnog Mapper downloaded, installed, or installed was trivial downloading the database, and now